yesterday we learned about buoyancy, and do you guys remember the formula for buoyancy? That is probably one of the biggest takeaway from it. Okay. So the buoyancy is rho Vg, right? So you want to learn this, and also put in some subscripts as well. Don't be afraid to do that. That is a very good way to help yourself understand better what each variable means. Okay, there's so many times people can recite formulas, especially in series students. One common problem that, in my experience, students encounter is I'll ask them, what is kinetic energy, and or what is gravitational potential energy, and they'll be able to recite, oh, mgh. Cool, but they don't know how to apply it to the problem. They got stuck. I know that formula, but what do I do here? Or they will be plugging in the wrong things. The h, for example, they might plug in a positive number when they should be plugging in a negative number, because they just think, oh, h is height, and they didn't realize I need to think about height from where, you know, that kind of thing. I'm making a somewhat arbitrary example. So knowing what the variable means is more important than knowing what the variable is, right? So that's why in the exams and in the tests that you'll see, if we ask for definitions, it's basically testing your understanding in the short answer questions, is to know what every symbol means. Just to save time, I'm not gonna rewrite this, but that is the logic behind it. Now, I have thrown this formula to you yesterday, but I have not answered why, okay? So let me do that now. And this is actually, the whole explanation is called Archimedes Principle. And it's actually a piece of very beautiful argument. It's one of a very genius philosopher, thinker in history who was able to come up with this. And as I go through this, I'll require you to have a little bit of imagination as well to be able to understand this properly, fully. And you'll hopefully appreciate how clever this argument is. So we want to find a buoyant force on something. Remember, we were trying to address why do things, let's say something is floating. Let's say I have a piece of wood floating, just hanging in equilibrium halfway over here. And we know that there's only contact forces. Remember my universal foolproof way of doing free body diagrams and understanding how to find all the forces in order to find the motion of particles. And as a result, answer almost everything in physics, right? That's the big picture. So we want to find all the forces on it. There's only that all forces can be classified into contact forces and non-contact forces. So here, the only thing in contact with it, right? So as what's in contact, what's touching it is the water. Except for that, there's nothing else. So you're done with contact forces, and now you need to analyze the non-contact force, which is gravity. Gravity points down. So without the water, it will fall down, obvious. So what makes it float? The only answer is it must be the force from the water. Hopefully, first understand this argument, right? So you understand there must be a buoyant force pointing up if it is floating. And this force must be from the water. So one thing I mentioned yesterday, but I want to put a star over here and re-emphasize. This is one thing you really need to understand about forces, is don't just say something has a force. That is in principle not a complete sentence. Every time I challenge you, let me put 2 stars over here. It's so important. Every time you hear a force, you need to ask yourself, the force is on what and due to what, okay? Or I can use different words. I can use or on what, from what, or on what, by what, on what, due to what, you know, different, it means the same thing, right? Just different way of saying the same thing. But you must have sort of a source. You have the object, right, and the source, okay? So in the case of buoyancy, so buoyant force is the force on, buoyant force, the definition of that is the upward force on any object due to surrounding fluid. Right? Okay. So let's go back to our piece of wood. My question is, assume I haven't told you this magic formula of rho Vg. How would you know? Archimedes thought of this. So this is his logic. Imagine you have the same piece of wood. Sorry, imagine you have the same volume of that wood. Let me just trace out the perimeter of this wood, right? So this volume, assume I'm just tracing out this exact same volume of water, and imagine I can drag this water out without the So, okay, so here there's a piece of wood here. Here there's no wood. So I dragged a piece of water over here. So this piece of water, let me actually make it blue. So this blue part of the water, this is the genius part, is floating, right? Do you agree? So this water is here. So it is floating. This part of the water is not sinking, because if this part of the water is sinking like this, then what happens? If it's sinking, then you would be left with a vacuum. You're left with a little bubble in the middle. The other water will rush in, right? It will start rushing in. But if the other sides of the water rush in, if we push our logic through, if they start rushing in, then they will leave other gaps over there, and then the other water will start filling up. And if that is the case, are you saying if I leave a cup of water here, the water will start circling and cycling and boiling on its own? That's clearly not what's happening, right? So the water is just suspended over here, right? The water is floating. All right, so what can we deduce from this is, if I draw a free body diagram, you now start to realize how much we love free body diagrams, which is arrows of forces starting from the center of mass of the object of interest. What is the forces over here? What's touching it? The surrounding water. Okay, we learned that there's some buoyancy force, okay, which we don't know. And that's it, right? So, and then there's a weight. But this must equal, because this water is floating. Okay. So since the water is, let me call that the water blob, is floating, then B must equals, remember, we still don't know what B is. That's our goal to find out. We don't have the formula yet. It's equals to the weight of that blob. So the buoyancy on the blob from the surrounding must equals to the weight on the blob, right? So the weight is the force on the blob from or due to gravity. That's what weight is, okay? For you guys taking quick notes, this is the symbol since. If we reverse that, that's the symbol therefore in mathematics. It's very useful for physics note taking. Yeah. Okay, so let's push this logic through. What is the weight of the blob? Well, it's the mass of that blob times gravity, mg. All right, and stick with me for a moment. The mass is the density times the volume, right? Remember, density is mass per unit volume. So mass per unit volume, so that's how much mass you have per 1 unit of volume. So if you multiply by how many volume you have, that's the mass, right? So that's the density of the blob times the volume of the blob. What's the density? So the density of the blob is basically the density of the water, right? And the volume is that volume of that blob. I'll just keep it as that, times gravity, okay? All right, so that's the first out of the 2 parts of the argument. The second part is, now let's go back to the piece of wood and ask what is that buoyant force. And the argument, the conclusion of that argument is, this buoyant force here must be the same as this. Why? It's what I emphasized over here. Because forces on an object is due to surrounding fluid. So whatever is supporting this wood comes from, what is the source? The source is, right? The source is really from the surrounding fluid. And the surrounding fluid does not have a mind of its own. It does not care what it is pushing up, whether it is pushing up the blob of water or the blob of wood. The surrounding fluid has no mind of its own. It's going to exert the exact same buoyant force. This is the argument that says the buoyant force on anything, as long as it has the same volume, because it does depend on sort of the volume, as you can realize, is this formula. It's rho of the fluid, right, water or the surrounding fluid, the volume of that. That's the only thing it depends on. It's the volume of that. And G. Does that make sense? That's the argument of why this formula is true. Let that sink in. Let me know if there's any questions. Okay. All right. While you're thinking, just to explain that a little bit more, is buoyant force is the water supporting the wood or anything in there, right? So if the think of you trying to support, trying to hold up a baby. So you are providing an upward force to the baby to counteract the weight of the baby, right? The upward force and weight, like that. You're trying to do that. Now, if you are supplying, 10 newtons, if your maximum ability is to produce whatever 100 newtons or whatever amount of force upwards, it doesn't matter who you're holding up, whether you're holding up a baby or if you're trying to lift up, I don't know, the rock. right? So you probably couldn't, but you are going to exert the exact same amount of maximum force on whatever you're holding. Let's say that it's actually, there's a hole underneath over here. For the baby, you will be able to suspend it. You'll be able to cause the baby to float in air. For the rock, his weight will probably win, right? Your upwards force is going to be tiny, right? But my point is, this length is going to be the same as this length. This magnitude is the same. The fact that he sinks down in the hole or drop down into oblivion is his own fault. It's his weight. It's nothing to do with you. So you've done your best, right? He falls down due to the weight. So if I have piece of metal over here, the metal will have a buoyancy force, and the weight, does it sink? Yes, it will sink. So the fact that you put a piece of wood over here and it floats, and you put the metal over here, it sinks, doesn't mean that the water doesn't care. The buoyancy force doesn't care what it is supporting. It is providing the same buoyancy force, and the only thing it cares for is the volume. Okay. Let me mention one thing. I'll get back to that. Is just to take care of one more special case. What if it is floating sort of halfway, right? So you get this problem in your test. What if you have a rock like this? What is the buoyancy force there? So the way to analyze this, I can do this now very quickly if you understand the logic, is go back to the pure water case with the same amount of water, and then trace out the perimeter, trace out the volume that is submerged in here, and look at this blob of water, right? And the argument now, it repeats itself. This blob of water, blob number 2, floats. Agree? That means the buoyant force over here equals the weight of the water of this, let's call this blob again. So now this rock is very heavy, right? A very long weight and a very, the buoyant force, now that you understand this B1 is the same as B2, right? So my question is, what is B1? Well, B1 is the same as B2 as my argument went, right? And B2 has to equal, so because this is the same, because since the surrounding fluid can't tell what it is holding, right? Whether it's holding the blob of water or holding the rock, the fluid can't tell. It's if the fluid is trying to support the rock, create a buoyant upward force, it's going to do the same thing, whether it's supporting the blob of water or that, just like that baby. And this equals to this because the blob is floating, since the blob is floating. Okay. And this equals to mg, m of the blob of g, and this equals to density of the blob, the volume of the blob, g, and equals to the density of water, the volume of either the blob. So this can be either the volume of the blob or the submerged part. You see where the submerged come in now, right? It's a submerged part of the rock. So it can be submerged part of the rock because these two are the same, right? Times g. And there you go. It's a one-line proof. Okay, good. All right, so just to quickly test your understanding, consider this. If I have a bowl of water and I put in a piece of wood over here, a piece of aluminum, and a piece of lead. Okay. Now, I will ask you 2 questions. Which one has the largest buoyancy? Question number 2, will each of them sink or float? Okay. Yes, I can scroll up a little bit. Okay, meanwhile, think about this. I'll give you 10 seconds. Which one do you think have the largest buoyancy? Just to give you an idea, the density of the wood is the least, the density of aluminum is second, the density of lead is the most dense, it's heaviest. Okay, let's say they're the same size. All right, any answers? Try to type it in the chat. Which one do you think the buoyancy is largest? All right, well done. That's a trick question. They're all the same. Very good. Because if we study our formula over here, right, the only thing it depends, well, it depends on 3 things, technically. It depends on the density of the surrounding fluid, which is the same for this case, the volume, which is the same. I didn't specify, I should say that, right? And the gravity. So they're all the same. All right. Now, which one will sink or float? Let's start with the wood. Will it sink or float? Anyone on the chat? Good. How about the aluminum? Just to give you an idea, the density is, this one is 0.6 times 10 to the power 3. This one is 2.7 times 10 to the power 3. This one is 11.34 times 10 to the power 3. These are the densities. Remember, water is 1,000. Water is, density of water is 1,000. 1 times 10 to the power 3. So aluminium, will it sink or float? Good job. And the lead? All right, that's obvious, right? Sink. All right, good. So this just reiterates what I have said, and this wraps up the discussion on buoyancy. Okay. So one thing I won't go through an example specifically, but I encourage you to do some reading. Is read what the example in the textbook. I forgot the reference part, but it's in chapter 13.7 on Archimedes Crown. So this is the very famous, I think maybe a lot of you already heard about this story when you're a kid already, the Archimedes Crown problem. And try to go through the solution, the example in the textbook. Remember, my job in lecture is not to tell you everything you need to know, but to tell you what you need to know, and you go and learn that. So look at that. That's that is one of the most famous legendary example where the story goes, where the king at the time was telling Archimedes to find out if the crown is real gold or not. So the problem is, all right, if it's real gold or not. So if you have a block of gold, let's say you know the density of gold. But the problem with a crown is it's not regular, right? So if you have something nice like a square, a cube, then you just need to take, you have this, you just have to take the mass of this cube, divide by the volume of the cube, because you can just measure the volume by measuring the dimensions like this, and then calculate this, and then compare, does this equals to gold, right? That's easy. However, if you have something shaped irregularly, like a crown, how can you find the density? How can you find the volume? So you can probably weigh the mass of this thing. You can put it on a scale like this, and let's say the scale reads 14.7 kilograms, right? Like that. All right. So that's the actual weight. Actually, one thing you learned from yesterday is that's not really the actual weight because it's surrounded by air. But hopefully, you also thought through the example. Is the air is so less dense, so sparse that it doesn't really change a lot. So the difference between the actual weight and apparent weight due to the buoyancy of our air is very, very small. So we can treat that as negligible. And that is why we always say it probably changes the first decimal place. Instead of 10.1, it's 10.2, something like that, right? So overall, it doesn't make too much of a difference. If you're doing engineering, if you're trying to build a bridge or something, right, to withstand some wind, or you have to take care of that. But the concept is the same. There's nothing new physics in terms of that. So now you put Archimedes one day realized you put it inside water, you can measure that again. It says something like 13.4 kilograms. Obviously, it's a little bit lighter because of buoyancy. And now you can set up to Newton's second law, and you can go and solve and go and actually calculate out what is the density of the crown. And you can read the chapter and find out what was the end of that story, if the crown is real gold or not. And of course, there's that legendary story where he was taking a bath when he came up with this idea of submerging it into water to find its buoyancy this way. And he shouted the famous words, "Eureka." Okay, good. So let's move on to now. Having wrapped up that chapter, we'll move on to static fluids. So now we I posted an interesting question in the beginning. You see that I didn't follow exactly the chapters the textbook go, and because I want to, first of all, we were doing a 3A review, and basically, if anyone was scared of 3A, how much material you will need, there's a little bit more from 3A you will need, but what I summarized from yesterday's hour is basically 80% or at least 70% of what you need from 3A. So if you review that lecture and you understand how to, basically, if you know how to do free body diagrams, you know 70% of what is needed from 3A in this course. Okay, so make sure you master how to do that procedure. So having discussed that, it's natural to start discussing buoyancy first. So now let's go back and go and look at static fluids. So we want to study other properties. What do we want to learn about more? Okay, so the reference chapters for today, I will actually post all these reference chapters a day before the lecture on the Canvas page. So if you want to skim through it a little bit first and do some pre-reading, you're welcome to do that. Or if you're doing review, you can refer to this. Every time I start a chapter, I'll write down the reference numbers. Okay, so the goal over here is just to learn more about fluids. And by the end of today, basically one thing I'll be able to show you is very quickly, you actually find out a way how to calculate how heavy your car is. And by the end of today, hopefully you also learn one thing is how do you lift up your car with one finger. So that is a very powerful application of this. So we'll see how that works. Okay, but let me comment on this first. Real fluids are very complicated. In fact, it's so complicated. If we actually till this day, in the forefront of science, we still do not know a way to completely model real fluids. It is that complicated. In fact, it's so difficult that it's voted one of the seven most difficult. It's called the Millennium Prize Problems. I don't know if anyone of you have heard about this. I'll scroll up a little bit in case someone is copying there while I talk. There is this Clay Mathematics Institute, a very respectable math institute in the world, and they came up in the millennium. In the early 2000s, they were surveying all the most difficult physics in mathematics and finding a complete solution, a complete model, accurate model to model real fluids. It's actually one of the seven. And if you actually solve that, it's still active under research at the moment. And if you're able to solve that, you actually get a price of $1 million US. So that is how difficult real fluids are. So obviously we're not going to tackle that problem, otherwise I wouldn't be here. What we're going to tackle is an idealized version of it. And now before you get disappointed, almost 90% of the time, this idealized version is a great approximation to everyday life. So it's only the other 10% that mathematicians really want to get a great handle on it and want to get a full solution, because we know it's very amazing. We know, if you ask me about, do I know how to analyze the motion of particles, single atoms? We know that to a very good degree. Right? We have very good models, very complete models on that. And if you ask me to model galaxies and planets and clusters in the cosmology, we have very precise, very great models about that. But fluids, something that takes up 60% of our Earth, is something that is most mysterious to us. We still don't understand that. This is a very interesting mystery, right? However, we wouldn't have all the technology and science if we don't even have some simple models. So we do, and in fact, they work very well. So those are what we're going to tackle. And the first thing I need to introduce is, what do we mean by ideal fluids? And there's three criteria. Number one, it has to be incompressible. So I want you to think about if you have a glass of water and you put a lid on top that you can push down. Can you squeeze the water? Not really. You can actually squeeze a tiny bit, to be honest, right? That's the part, that's the approximation part. But in most cases, I think you will agree as well as I do that it is very good. It's a good approximation that to make it perfectly incompressible. That is also okay. Let me say the next one first. And the next one is irrotational, and the last one is non-viscous. What do these mean? Okay, non-viscous. Let me talk about that. So viscous is coming from the word viscosity. Hopefully everyone understands above. I'll zoom back in. Viscosity is basically friction. It's basically friction for fluids. It's a fancy word for friction for fluids, right? So non-viscous means that it has no internal friction. Right? No surprise to people. That's number one physics approximation, assume things don't have friction. So that means that water, as you know, fluids take the shape of the container, and we assume that it is so flexible, it can take the shape of the container instantly and very flexibly. There's no resistance at all in taking up that. So again, you see that is a very reasonable assumption. And irrotational is basically saying there's no turbulence. So if you've been on a plane, right? So turbulence comes by when air starts rotating and creating vortexes. That is causing the most, this number two is actually causing the most difficult, and actually 2 and 3 causes the most difficult way to analyze real fluids. If we say a fluid is irrotational, that means the fluid is undergoing a steady flow and no turbulence. Okay. And incompressible, another way to say that is also you can, so this is the symbol for equivalent, right? You can say that the density is constant. So this is just a reminder, this is the symbol for equivalent to. So saying things are, a fluid is incompressible, it's also saying the density is constant. Why is that? Quickly, because if you cannot compress something, that means your volume is fixed, right? If you cannot compress something. But if you have, okay, so let's say this is a fluid, right? So this is a fluid. the volume is fixed, but the mass is always fixed because there's a conservation of mass. Mass cannot be spontaneously created or destroyed in our everyday life. So if the mass is also conserved, then since density is mass per unit volume, if the volume is fixed, the mass is fixed, the density is constant. In more realistically, what we're talking is, or more applicable to us is, when we talk about the density of the fluid, remember when we look at buoyancy, we need the density of fluid. We didn't care, are we talking about the density of this point or this point or this point or this point or this point? It's constant throughout the fluid. Okay? So these are the assumptions we're going to make. In real life, there is tiny variations in density. For example, if you look at air, the atmosphere, it is more dense here and it's less dense in the atmosphere. All the way, it gets less and less dense until it goes to a place where it's practically nothing. That's where we define the perimeter, the end of the atmosphere, and then everything outside is outer space, right? So you see density does change in real life, but if you're jumping up and down in your everyday life, even, you probably, it's a good approximation. In fact, criteria number one is very easy to relax. If we know how to solve number one, even if it's not constant. It's number 2 and 3 that is the most difficult for real fluids. So in fact, also you see that number 2 and 3 actually has to do with friction and also flow. So that's to do with dynamic fluids. We'll return to that a little bit more tomorrow. So really the main criteria we are concerned for today's purpose for the next 45 minutes is the incompressibility criteria, okay? So let's introduce the next concept. Okay, so let's first define another concept called pressure. You probably already know what it is. It's nothing too new, but we'll put this officially down here. The definition is force per unit area. So one comment is pressure is a local property, what we call a local property of some substance, of a substance. So what that means is when we talk about pressure, we need to talk about pressure at a point. I like to always emphasize what I call fine prints. So whenever you talk about some physics concepts or quantity, so quantity is a word that we always use, basically just means a certain physics concept. What I underline there is what I call fine prints. There are things that sometimes we don't say every time explicitly, and it's kind of understood. That's why we don't say it, but it's very important to know. And if you don't understand there is a fine print, you will run in trouble. For example, like force. The fine print of force is, I'm not going to write it out. The fine print of force is, every time you say force in principle, you have to say on what, from what, right? These are the fine prints of it. If you don't say it, that's actually an incomplete sentence. It's almost like saying, today I went to where. You need to say today I went to someplace from someplace or something like that. You need to complete the sentence. So that's what I mean by fine prints. Okay, all right. So in equation form, as you know, when you are memorizing definitions, you can either go with the word. You can define things in words, or you can define things in math. Okay, so it's force per unit area. What's that little bracket over there? Okay, so this is actually the force acting perpendicular to that area. So that's a perpendicular symbol, right? Like an inverse T. So force acting perpendicular to the area. And A is obviously the area, P is obviously the pressure on that area. Okay. What's the SI base unit? And why do we care about SI base units, as you see, is because there's a very quick trick, and it works 100% of the time for problem solving. So it's very powerful. Is when you, this is how I do all my physics problem. When I look at it, I first convert everything into MKS, into SI base units, meters, kilograms, or seconds, or things that are made out of meters, kilograms, and seconds. And don't confuse yourself with using the CGS system. If you use the MKS system, after that's my first step. I convert everything, and then I plug in just purely the numbers. And in my equations, I don't have to cancel the units; they will automatically work themselves out. It's magical. And then at the end, you just have to put back in to the SI units. So it's called Pascals. So by the mathematician Pascal. This is identical to newtons per meter square. Basically, look at the formula, it's force per unit area, right? So force is newtons, meters square is area, so newtons per meter square. This 3 strokes is what mathematicians call identical to. Right? So this actually 3 different equal signs mathematicians always different they will use. Right? So the first one means equal to, the second means identical to, the third one means it's defined as. Okay? Defined, identical, equal. Of course, if it's a definition, I can say it's equal. But sometimes, so a lot of times I will just use the equal sign. But when I want to emphasize something, I want to emphasize that Pascal's is identical. It's basically just another name for, it's a lazy way to write newtons per meter square, right? So if you go all the way back to the MKS, newtons is, find the formula for force, F equals ma. So m is kilograms, a acceleration, meter per second square, right? So the whole thing is actually kilograms per meter square, so per meter per second square, like that, if you simplify that. So you can always reduce composite SI units all the way back to base units like that. Okay, so let's do a quick example. And let's try to find the mass of our cars. So imagine you have a car over here. Is there a clever way to find out how heavy it is? So here's a nice way to do it. If you look at your tire, it will actually tell you what is the pressure, the air pressure inside the tire. And the standard ones are, so if it doesn't say, you can also plug in a barometer into it, and the gauge will tell you that it's standard things are roughly 32 pounds per square inch, PSI. So all those pressure is laid on 4 wheels, right? So actually on area over here, I should specify, it's the contact area. So where the contact forces, pressure has to be, does it have to be? Yeah, I think it has to be a contact force because you're pushing on a certain area, right? So what is the contact area that the pressure of the car is acting on? It's the area touching the ground and the car, all right? So here's how you can do a quick analysis, right? So first of all, pounds per square inch, those are all imperial units. So let's get rid of imperial units and join the modern world to use scientific units and metric system. So first of all, 1 PSI is, you can look this up in the book. If someone had a question before who asked me, do you need to know these unit conversions if you're given some obscure units in the exam? No, you don't. If, for example, if you're given any imperial units or something that is not a metric or not a scientific SI units, we will give you the conversion. And that's one reason why I don't want to use responders for the final exam, is when we write exams, sometimes we do forget. And then if students ask a legitimate question and say, oh, what about this constant, can I get that information? At least over Zoom, you can message me and I realize, oh, I should give you that constant, immediately fix the exam. With responders, there's no way for me to communicate with you, right? So that's one reason. We'll talk more about final exam on the policy in the future. Okay. All right, so 1 PSI is 6.895 kilopascals. So kilo is 10 to the power 3. That you do need to know. Okay, so how to, let me take this opportunity to also to demonstrate how I do unit conversions, right? So most of you hopefully are familiar with it, but I'll show you my quick way. It's a little trick of doing it. It's this. First, write bracket and write an extra 1 over here. So treat this as 32 times 1 PSI. So does that make sense? Yes, 32 PSI is 32 amounts of 1 PSIs, right? So 32 times, I can write a time symbol if I want, of 1 PSI. Now let's look over here. 1 PSI is exactly, so this is exactly this, 6.895 kilopascals. So I can replace that parentheses with 6.895 because this is exactly this. Now I just have to do the math and plug that in the calculator. So you punch that in the calculator and you realize that's around 220. And now you're just left with this unit. That's a very nice way to convert units very quickly instead of writing something over something, you know, and start canceling things out. Don't get me wrong, that's completely fine. I'm just showing you an alternative way. If you like it, I recommend it. If you're uncomfortable with this, no worries. Okay. All right, so now we basically have our pressure, but that's the pressure on one tire, right? So what we really want is the whole pressure of the car on it. So if we draw a free body diagram, what's really pushing on it is the weight of the car. So if we look at our formula, pressure is identical to force per unit area, right? So our force is the weight, right, of the car is pressure on the wheel, pressure between the weight and the ground, right? That's the contact area times the area. So each of the tires have the same pressure, 220 kilopascals. So kilo, let me write 10 to the power 3. So that translates it to the SI units because I get rid of the kilo. Now it's pascals because pascals is the base unit and I don't need to write the pascals now. And then how many areas? I have 4 wheels, right? So I actually, the contact area, the pressure is 220. The area is 4 times the wheels, right? So let's just quickly estimate what it is. So let's say it's 10 centimeters by 10 centimeters. So if you take a ruler, imagine your car contact each wheel, how 10 centimeters is roughly that much. So imagine a square of that. That's roughly, it might be around like 12 times 10, more than 10 times 10, but let's just do a rough estimate, approximately over here. All right, so convert the units, etc., plug that into a calculator, and this is what I got, 9653 newtons. All right, 9653 newtons. What is the mass? The mass is taking the weight and divide by gravity, acceleration due to gravity, divide by 9.81. And so that's roughly dividing by 10, right? So this is like 10,000 newtons, divide by 10. So that's 1,000 Newton. I'm just, because everything is an estimate at the moment. So, oh, sorry, 1,000 kilograms. So I'll just say approximately, I'm not gonna worry about it. And 1,000 kilograms is exactly 1 ton, right? That's 1 metric ton. So you probably heard a car roughly weighs a ton. So by measuring the wheels, now you figure out a way you can actually find out how heavy your car is. All right, now let's specifically talk about fluid pressure. Okay, so here, let me give you a very useful formula. Throughout the course, you'll start to see not all formulas are created equal. Every time when you look at a formula sheet, there's a something equals something, right? A lot of somethings equals some things. But actually, you'll start to realize some of them are actual formulas and some of them are definitions, okay? And this is a formula. Slowly, you'll start to pick up what's the difference between them, right? So what the useful formula is for is the pressure due to fluids. So earlier, in that example, that was the pressure due to the car. But now, what is the pressure due to fluid? That means if you're standing here and you have a pile of fluid on top of you, that's not too realistic, but in fact, we do have some air on top of us. What pressure do you feel, right? Or slightly more, less cartoonish is, if you have a beaker of fluid, what is the pressure at the bottom of the fluid? Or if you have the ocean of the world, what is the pressure at the bottom of the ocean? So there's a formula here, which is also worth committing to memorization. It's rho GH. Okay. It is a little bit similar to a buoyancy, so don't get that confused. And that's the rho of the fluid. G is gravity, right? That's the density of the fluid. And H is the height of the fluid. So this is the H, if you're interested in the pressure at the bottom of the fluid. Okay, so this gives you the pressure due to the fluid above it. Maybe I should say due to the fluid above a point. Remember the fine print, pressure is about a point, right? So this is the pressure above that certain point due to the fluids. Since this is a lecture, I'm just going to use arrows to define my variables and symbols, and the exam write it out a little bit nicer. But actually, even if you use arrow, that is fine. I just want you guys to define it. Then the purpose, of course, is to understand the variables, not just the symbol. Okay, and let me give you a little tip to remember this. It sounds a lot like, remember gravitational potential energy from 3A, right? So it sounds like mgh. So that's a good way to remember it. It's rho gh. And in fact, there is actually a very close link between between the gravitational potential energy and the pressure due to the fluid. But imagine if you divide this by volume, right? Mass per unit volume is density, and you'll get rho gh. Right? So there is a definite connection here. So that's how you can remember this. Okay, why is this? Where does this formula come from? Again, the answer is always, that's why I spent a big part of the yesterday's lecture reviewing 3A, because the answer is, again, free body diagrams. Okay, so let's assume I have this fluid over here, and I want to find the pressure at this point. How do I find it out? So let's see, what is pushing on this point? Well, it's all the fluid above, right? So let me find the center of mass of that fluid, that's here, and draw a free body diagram, all right? So there is definitely the non-contact force of the weight. Okay, that's what's pushing it down. And then there's the normal force of the body, which is pushing it back up so that the fluid doesn't actually go down the earth, right? It's held inside this container. But that's not what I'm interested in. That normal force is pointing up. That doesn't contribute to the pressure. The pressure is the force pushing down on that point, right? The normal force it's pushing the fluid up, it's not pushing the fluid down. So only the weight is contributing to the pressure. All right, so the weight of the fluid, what is it? Well, it's mg. So I want to find the pressure, right? So pressure is identical to, because from definition, it's defined as force per unit area. What force are we talking about? We're talking about the weight of the fluid on that area of this bottom part, right? So all the weight on this area over here. Okay, so what is the weight of the fluid? It's mg, the mass of the fluid. And this is a trick, as you see, we will use over and over again. We always make use of this relationship, mass per unit volume is density, and sort of shuffle things around. And it's a very, when in doubt, basically try to see if you can squeeze that trick in, right? And you'll get this, and this, the volume is basically area times height, right? The bottom area, the base area times the height, like this. So if we plug this back in here, you'll see that is area times height times g, like this. That's the weight divided by area, and voila, you'll get the formula we need. Okay, so that's where that formula comes from. So a quick studying tip for formulas like this in the exam, almost most of the time, you will not be asked to derive these formulas. You will not be asked to prove or derive these, both for the buoyancy formula that I did in the beginning of today and also this one and most of the other future ones. What you will need to know is how to use this. Of course, this is a lecture. I'm supposed to teach you concepts, so it's good to understand this as well. And don't easily dismiss this, because if you understand where things come from, because what we're going to test you is test you on applications of this. And if you know where things come from, it makes the application much easier. Sometimes students bypass completely trying to understand where things come from and trying to skip that step and doing the more difficult step in principle, which is applying that concept without knowing where things come from. That is actually making your life more difficult than it is. To make your own life easier, it's actually easy. I think it's not too difficult to understand this, right? Spend 5 minutes there at this, ask people on Piazza if anything confuses you, and understand this. It will make solving physics problem a lot easier, especially for those who want to get an A. I think it's not too difficult over here. Okay, so quick question to test your understanding. If I have, let me give you 4 containers like this, and I want to ask you the pressure at the bottom. So let's call that A, B, C, D. Can you quickly guess which one has the greatest pressure at the bottom? So if you are being scientific, you would apply the formula and think that through, but just want to get an intuition. Nothing is graded here, right? To see what your intuition tells you. Let's compare first A and B. In the chat, just between A and B, let's do 2 by 2. That's easier to compare. Prop it up. Which one have a greater pressure at the point A? So which one is pushing down stronger at point A? So let me clarify. The base over here, I'm trying to make them equal. So this does have less water than this, okay? So B does have less water than A. Pop it. Give you a few seconds. Good, a lot of you say A. That is very natural. Someone said the same. That's interesting. Let's look at C and D. Actually, look at A and C first. Let's compare A and C. You don't have to type this out. Just think, what does your intuition tell you? You probably sense that this is a trick question and the answer is the same at the end. Let me give you a spoiler alert. Yeah, they're all the same. But intuition tells, probably you feel that A is probably more because it has more water. Or alternative, you might think that C is more. There's more pressure on C because it's focused, all of that water is focused on a small area. The area is smaller, right? Now, I'll get back to that, and then let's compare C and D, for example. Again, C has more water than D. The point I'm trying to make is, let's say this is the same width down here, right? Then you would think that C has a higher pressure than D. But someone already probably guessed that all of them actually has the same. Okay. Now, this is a very important takeaway. Important takeaway number 1 is the pressure at a point only depends on the thin column directly above it. So what I mean is this point over here only really depends on a slice like that. Because if you look at the formula now a little bit more, let's analyze this a little bit more scientifically. What's going on here? Sure, actually, the whole fluid, yes, it is pushing down on here. But notice, the bigger the chunk of fluid, also the bigger the base area. So if you look at the formula over here, yes, the more fluid does increase the weight. I agree. So that was what suggests that one of those bigger flask or bigger beaker that you thought that there's more pressure. But at the same time, A increases. And does A increases twice as much or 3 times as much? No. A increases the same way the weight increases with the base area, and they cancel out perfectly. So what's left is just what's directly above it. So let me use normal English to explain that is the more weight you have, the more water you have, it is more spread out at the same time. And mathematically speaking, that spreading out and the larger weight cancels out perfectly, okay? And it really just depends on the height directly above it. So if you look over here, as long as they have the same height, which is what I try to draw with these diagrams, right? Whether it's a thin or thick, they have exactly the same pressure. Takeaway number 1, all right? Let's test your intuition in another scenario. Let me fill up the liquid like this. So you have experience, if you have a channel like this, you pour water in it, they'll sort of go up roughly to the same height. And then let me label 6 different points here, and you can think about which one has the greatest pressure. Point 1, 2, 3, 4, 5, or 6. Okay, so the answer is, if you learned the takeaway from number 1, it depends on the depth, right? So first of all, what we learned directly is 3 and 6 must have the same pressure. I agree. And now, how about 2 and 5? They will be the same as well. Good job, Jada and Michael. Let's look at 2. The lesson number 1 was, how should we analyze this properly? Is we should look at the fluid directly above it. That's what's contributing to the pressure at the point. So the fluid directly above 2 is this part of the fluid. The fluid directly above 5 is this part. Like, technically, I need to shrink that width down to 0 with just that thin little line of fluid, but you get the idea. So 2 and 5 has the same pressure as well. And how about 1 and 4? Yes, they're the same because if there's nothing on top, let's say there's not even air, right? Let's say this is a flask in outer space, then both of them have 0 pressure because nothing is on top. If this is a vacuum, then that would be 0. But most likely that's not a vacuum, so it's probably air, so there will be some atmospheric pressure on top. What that means is there's a chunk of air on top of this. So this leads me to takeaway number 2 is equal depth, equal pressure. These are easy, these could be one of the short answer questions in tests or exams, by the way. You could easily ask which one has the greatest pressure or whatever, something like that. Or you could ask between the 0.3 and 0.4, which one has the greater pressure. I think you can answer that now. So one more. What if I have a column like this, and then another column that is slanted like this? Which one has a greater pressure here? So if you follow my logic, the column of fluid directly above it, which one do you think? So if you follow the logic, it looks like A, right? But then what's interesting is B has more liquid, because if it's slanted, imagine the extreme, you make a very, very long pipe, right? That is slanted somewhere else compared to a very short pipe. Now from lesson number 1, we realize, from takeaway number 1, we realize the width of this pipe doesn't might as well. So it might as well be a straw or whatever, and a very long pipe, or we can, right? So one have less liquid, other have more liquid. Turns out what's interesting, they balance each other. For now, I'll just give you the quick answer, and the answer quite magically is the same. So what you want to analyze is the perpendicular height above it. It basically, just to give you an idea where this comes from, it's due to the definition of pressure. It's perpendicular force over here, okay? And that makes a difference. Okay. So maybe I'll encourage you to think about this yourself. So let's talk a little bit about atmospheric pressure, because we just mentioned over here on top, if it's not vacuum on top, there is an atmosphere. So if I have a liquid and I want to find the pressure over here, the pressure is not 0. The pressure is equals to the pressure of the column of air directly above it. So roughly speaking, air is also a fluid, right? So roughly speaking, the column of air directly above it, what is the formula? What is that very useful formula that we just introduced for pressure due to fluid at a point? It sounds like mgh, right? But rho gh. Okay, so rho gh. What rho? Should we use rho of water or rho of air? We should use a rho of air because we care about the air directly, the pressure from directly above it. All right, G is G. What H should we use? Well, we need to look at how high this air goes. It will go all the way up to the atmosphere, right? So this height is the height of the air all the way from there up to the atmosphere. And if you plug this in, the air density is 1.29, gravity acceleration 9.81. The air, that is what you want to put in the height of the atmosphere, and it will give you a rough answer. Now, I want to say, I do want to say rough answer. I do want to emphasize rough answer because technically, as I mentioned, the density changes. The density is not constant for the atmosphere. If you go that far high up, it will gradually go to zero. So which density? What is the 1.29? The 1.29 is actually at sea level. So density of air equals, if you look at table 13.1 in your textbook, it has all the list of the pressures, density, sorry. This is actually at sea level. Of course, we're close to sea level, especially if you're in Irvine. So that works well. Even if you're on top of a mountain, it's a little bit thinner. It's not that different, but when you go a kilometer or 2 kilometers up, there'll be a very big difference. And also the temperature makes a little bit of difference as well. So at room temperature, so this is at roughly 20 degrees Celsius. It's around, that's around 68 degrees Fahrenheit. So technically this formula here, I need to put a caveat over there. I need to put a footnote. It's not technically correct. I need to use a more sophisticated one. This is requires a little bit of calculus, and it's not going to be examinable. So but I'll just give you the answer. So the answer, if you do the calculation properly, you can calculate the atmospheric pressure at sea level at 20 degrees at room temperature is 101 kPa. Do you need to memorize this? No. Anytime we'll give you this information. But if you solve a lot of problems, if you do a lot of practice problems, it probably is one of those useful numbers to keep in mind. Just like density of water is at 1,000. This is 101 kPa, right? So it's technically 101 and then 3 more zeros. More specifically, it's 101.3, but 101 is easier to remember. And with 3 significant figures, it's enough to do most of your calculations. So that is the atmospheric pressure. What can we learn from this? Here's the challenge. Can you calculate the pressure on top of your head right now? I know there's a roof on top of your head, but let's say you stand outside. There's this huge column of air. You know the pressure is, atmospheric pressure hitting here is 101 kPa. Can you translate that, estimate your area of your head and translate that into the force on your head? So I'll save this as a Piazza question for people to chime in the community to see what force you get. I'll tell you what I got. So it depends on how much what your estimate of your area of your head is. I got 4,000, roughly 4,000 Newton, round to one significant figure because this is estimate. Okay, so try this yourself. If I were you, I'll put a star in your notes so you can remember when you go through the notes, you can try this exercise. And here I want to make an extra comment. Notice the examples I give in lectures are slightly different from the examples you'll see in discussion session, which is closer to what will be done in exam. With the last few minutes, I want to explain the logic for this is what you want to take away from physics is when you go into the real life, no one is going to set up these very rigid exam questions like given the mass is 10, something is blah, blah, calculate something, right? That's only happens in exam. In real life, you want to take your ability to do logical thinking to solve real life problems. Some of you mentioned physics is about solving real life problems. That's absolutely correct. And if you walk on the streets, you never know. One day someone would ask you, hey, what's actually the force on top of my head due to this column of atmosphere of air? And you need to be able to answer that with your knowledge of scientific thinking, of this logical thinking. Or physics is a very good training to train this muscle of your head. What you need is 3 abilities to able to answer real life problems. Well, I guess this is as real life a problem as I can get. Number 1 is you need the physics concepts, because if you don't know pressure, stuff like that, there's no hope. So yes, you do need the hard skills, right? I call these hard skills. And then there's the soft skills. Number 2 is the logical thinking, is the way to think through it. Okay, I know the concepts. Many students stuck over here is they memorize everything from the textbook, they read it very well, but they struggle to learn how to think. So how do you help train yourself to be better at logical thinking? Is understand proofs like derivations and proof like what I did over here in explaining where the formulas come from. Even though it's not examined, because it's just for nicer for you guys. If you're a physics major, these are what we focus on examining and less about problems. We ask people to derive these things. But yeah, but even if it's not examined, so we don't want to give you that pressure, no pun intended, but still try to learn it, right? It's not that difficult, and give yourself 5-10 minutes, try to understand it. That will train yourself to do logical thinking, and it will help you solve problems better. And in fact, this is a much more important skill to carry in your future life after you graduate in the rest of your life. And the last skill is doing estimation. It's the estimation skill. This is what's a skill that is least talked about even with physics majors, to be honest, and it should be talked about more. Because when you go out to real life, a lot of times you need to, when you want to address a real life problem, you need to do some sort of estimates, whether it's your finance or a science problem or some medical issue. There is some degree of that. So you see, yeah, in this example, the examples I give over here utilizes all these skills all together, right? So let me introduce one more equation, which is called Pascal's principle. So his principle says that the pressure is always, the pressure will be transmitted undiminished throughout a fluid. So he noticed this. What that means in, let's rephrase that in normal English, right? In simple English, if I have a can of liquid over here, if I try to put a lid on top and then push down with my hand, right? Like actually push down and exert some external force on it. So I'm actually applying some external pressure on it. What is the pressure over here? And in simple English is the pressure at the bottom is equals to the pressure, the pressure of the fluid directly above, of course, which is what we already learned, just plus the external pressure on top exerted over here, okay? So if you have a beaker like this, and you want to find the actual pressure, the actual, or sometimes called absolute pressure, right? Not just the pressure due to the fluid, but the complete, total, absolute pressure at this point. It will be the pressure due to the fluid plus the pressure due to the air. So everything on top will contribute over here. So this part is rho GH, rho of the fluid, and GH. This part is P atmosphere, right? So the absolute pressure, or the actual pressure, is P atmosphere plus rho GH. So this is one example of how you apply Pascal's principle. And it leads to actually more general formulas. If I want to compare 2 points at the bottom and the pressure at a point above, let's say I want to compare the pressure between these. So the bottom point is the pressure on top plus the pressure of the fluid, which is, as we learned, right, that part is rho GH, and H is this part. So see how important you need to know where these things come from. Because if you don't know and you just say, oh, I memorized rho GH, having a formula sheet with you in the exam does not help you at all. Because this is the most common mistake I see when we give problems like this, to calculate the pressure at this point, and people will plug in the height of the whole fluid like this. Or they might plug in the height of this part, or anything crazy that people can come up with. That's all wrong. The only correct answer is this part, right? Does that make sense? Hopefully you understand, right, where that comes from. And yeah, this is actually a very useful formula, because often we need to compare 2 points. You'll see some of these examples in the homework and tomorrow's discussion session. This formula, bottom equals to top plus rho GH, is so useful. There's a name for it. It's called the hydrostatic equation, right? Hydro, water, static, at rest. So hydrostatic equation, what does it do? It's linking P bottom with P top. It's comparing the pressure at 2 different points with some liquid in between. But understand this is the pressure due to the fluid in the middle. So a lot of the times, you know, when we talk about pressure nowadays, so let's say if someone decide to, if you're standing here and someone is being just a douchebag and pushing on your head, trying to exert some pressure on you, and you want to find out how much pressure they are pushing on you, what really happens is, because pressures add up, like we just learned, they add up. the absolute pressure over here is the atmospheric pressure plus that external pressure, right? But sometimes we don't really care about the atmospheric pressure. We really just want to find out what the external pressure is. So if you put a scale on top of your head, you put a barometer. A barometer is device, barometer is a device that measures pressure, and you want to find out how much pressure this guy is exerting on you, so that you decide whether to sue them or not. Yeah, so you want to just find out the external pressure. You don't care, because if you go in court and then you quote a huge number with the atmospheric pressure, everyone will look at you and say, sure, there's like 400 newtons every day on my head. By the way, if any one of you ever feel like you're under a lot of pressure, you are correct. We are all under a lot of pressure, like literally. So that is not useful information. We deal with that everyday life, so much so that we don't even care about it. In fact, our body is so good at counteracting our atmospheric pressure that if you go in space, suddenly there's no pressure outside. The inside of you are still in atmospheric pressure. It's going to push right out and you're going to explode into flames. Well, not flames, but that's why people die in space. Let's forget about the suffocating issue. You'll have to worry about your skin exploding first. So atmospheric pressure is always there, right? So sometimes we want to subtract away that. So here comes the idea of gauge pressure. It's a weird term, I know. But gauge pressure is basically the absolute pressure, whatever, the total pressure. Sometimes I like to just call it the total pressure. Subtract away the atmospheric pressure. So that's the definition of gauge pressure. So sometimes that's useful. So when if you become a doctor, a lot of you are going into medical school and you measure people's blood pressure, and then you look at you wrap around their arms and then you look at the scale. That scale is actually measuring the gauge pressure. It doesn't take care. So you don't have to worry, oh, this guy is experiencing a lot of pressure from it. And that's where the name comes from, gauge, because you look at a gauge over there. Okay, so I'll leave this to the next time. This is just one final thing with 5 minutes to discuss, but I'll probably leave this to next time, is how you can utilize this to set up something like this. If I put some fluid over here connected by a tube, right? So they'll fill it in, so they're roughly the same height, right? And now I put a platform over here, and I put a lid over here, put a lid over here, and there's something called mechanical advantage. Using the idea of pressure actually gets transmitted undiminished with Pascal's principle over here. This is a very powerful application that you can lift up a car with just pushing down one finger. So next time I'll plug in some of the numbers to show you how much force you need to push down here to lift a car. You'll be surprised how little can do that. All right, so with that teaser, I'll leave it till next time. Thank you very much. Hope you enjoyed this, and we'll see you guys tomorrow. Welcome back to lecture 3. So today I want to talk about extra credits. How do we assign the points before we start? Yeah, so let me switch back to my desktop. Also, someone had asked me about lecture recordings. I have posted just this morning. I have posted yesterday's recording. So apologies for some of the delay. So let me just explain what was I doing. So I wanted, so partly, as I mentioned, I was trying, one thing I know that is useful for you guys is having little segments of the lecture instead of sitting through a whole 80, 90 minutes lecture in one go. So I know the best thing that will help you guys is actually little short videos of like 10, 15-minute segments. However, that will take time. So, I realize I'm probably asking too much of myself. So the next best thing I can do is utilize the chapter feature on YouTube. So if I upload it unlisted to YouTube, you can actually go, you can see the chapter timestamps of everything. Hopefully then you can select, oh, I want to look at this segment. So hopefully that's the second best thing I can do for you. I want to try to find a way to best do it to help you guys. And also watching back at also a small factor of me delaying is I'm just editing out some of the really poorly spoken parts, and just watching back myself, I realized how embarrassing this is. So I just realized, I didn't just realize, I know I always, speaking to camera is one of the things that is most uncomfortable to me. So this is me just stepping completely out of a comfort zone, and I realized me teaching it in person is so different than speaking to a camera. So it's not just the part that I feel embarrassed for myself. That is a small part, but the issue is I realize if it's very difficult to sit through, you won't learn well. And I want to make it easy for you guys to learn well as well. So I try to sort of chop out a little bits and pieces. I did so before I upload it that way. So that's that. But hopefully my goal is with everything, just like physics and anything in life, if you want to do well in something, it's all about practice and trying to improve every day, trying to think of a better way to say it's not just practice, but evaluated practice. So look at, it applies to your physics learning as well. So you do your homework and you don't just practice. Sometimes people say practice makes perfect, but you need to be practicing the right thing. To be honest, there's a better saying. It's really practice makes permanent. So if you're practicing the wrong thing, that's not going to help you at all. So what you want is you practice when you're doing your homework. I will actually talk a little bit about homework next time as well. Let me just say one thing is when you see if you do a homework and you realize you didn't get the right answer, immediately reevaluate yourself and look at what you did wrong. Try to think about not just getting the right answer, but think about why you got it wrong and try to learn the lesson from there. Okay, and how do I make it easy for you to do that is, as you can see, so these are the homework problems from the textbook, and a lot of them I've selected is actually odd number problems that I think is appropriate. As you see, almost I think 8 out of 10 or 7 out of 10 are odd number problems. And at the end, in the appendix of your textbook, you have the numerical answers to all of the odd number problems. Okay, so this is done on purpose because the homework is not really the purpose of my homework is not to show that you fail at solving something. And if you solve a problem, you don't know if it's right or wrong, you submit it, and then the TA grade it, and then say, oh, you're wrong. All right, thank you very much. That's not very helpful. So having the numerical answer, but not giving away a full solution, because as you look at the grading, you realize that if it's up to us, if we have unlimited resources, we'll actually try to help you try to grade everything in terms of quality, because that is really what we want you to learn from out of a physics course, not just getting things the right answer, right? Not just plug and chug. We want you to learn how to think like a physicist. That is, remember in lecture 1, that is our main goal. So grading things in quality is the best, but that is not possible for limited resources. So we'll just grade 1 out of each, right? So the numerical answer, as you see, is never the main point of learning physics. Only 1 out of 5, roughly, I always tell the students that only around 20% of the proportion is how much we care about you getting the right answer. 80% of the proportion of any solutions, we care about can you present logical thinking, right? That is what we want you to take away from the course. So having the numerical, giving you the final answer is not a problem for me. And in fact, it's encouraged that you look at the answer and you realize, oh, I didn't get it right. So what's wrong in my logic, and try to fix that and evaluate yourself. Right, so that's the philosophy for that. As you know, one will be randomly graded. You will see that some of them are even number problems. So it is very likely we'll select a one that without a numerical answer to grade. That's also actually to your benefit, because without the numerical answer, you don't know if I grade one with the odd numbers, you won't know, as in if I grade one with the odd numbers, you'll know how well you presented your steps and your logic, but it doesn't help you know if you did things right or wrong, because if you got the right answer, very likely you did something right, right? And then you still don't know the other ones that are even number if you did it right or wrong. So it's actually better for us to grade ones that so at the same time, we give you feedback on how well you did with the quality, and also did you get it right? So you can sort of almost guess which one will, it limits down the choice of which one we're going to grade. But I reserve the right to change that. Out of the blue, we can one day grade one of the odd numbers. I have, yeah. So just to keep that open. Okay. All right. So yeah. So evaluated practice. I hope. While you guys are learning physics, one thing I want to learn better is also online teaching facing cameras and talking about this. Hope this is not going to be the ultimate future of education, but it is still going to be a big part of it. So this is my goal. I'll try to get better, and thank you for sticking with me. I see a lot of you guys joining in and supporting me, so I really appreciate that. And I hope I get better all the way along the way, right? So halfway through or by the end of the course, it'll be much more enjoyable to watch a lecture than it is. Okay, so extra credits. So if you go to, I'm just going to the student view, so you see this is hopefully similar to what you'll see. I've just made the assignment available. I recommend you, because the way I set up the course, I recommend you to always switch it to show by type. Otherwise, it defeats the purpose of me spending hours to organize this. So this will make things a lot more organized. Then you can navigate to extra credit. So remember, the policy is if you post between 5 to 10 posts, whether it's a question or a reply or an answer or anything, right? I'm making that very, very flexible. So I want most of you to participate and most of you to potentially get the full 10%. And I think because everyone participating really helps the community as well. So I think it's really a win-win-win situation. Yeah, so, and if you post more than 10, you will get 10%. Okay, so let's click on this. Assume you're trying to request for 10%, and you'll see I have the instructions and also a request form. Okay, so if you click this, the instructions, basically what you want to do is to take screenshots of it. Okay, so it's very simple, just 4 steps. Step number 1, go to the assignment, click the request form. I have it pre-opened over here just to save time of launching the Word document. Okay, so you will get this Word document, and then just fill in your first name, last name, and then put in the screenshots of whether you're requesting for 5 or 10, right? So you don't have to put in more than 10. Okay. So if you like, you can start doing it now with the post that you've already posted, or you can do it all the way at the end. I think it'll probably just take you no more than 5 minutes or at most to take all the screenshots. Okay, so how do you take the screenshots? So on Piazza, there's a way to filter out everything that you have followed. Yep. So that means anything you post or anything you reply to. So what you do, let me go to Piazza. On the next to the search bar on top here, there's the gear icon. The settings, go in here and then navigate down to following. And here, these are everything that I have replied to. So I've clearly replied to more than 10, so I should get 10% as well. Yeah, so, okay, so for example, you will go and look at, for example, let's see, what's a good one? Definitions, good, like this. And then you can take a screenshot of that. So what your screenshot should show is 2 things. It should show your name, because if you post something, I'll get to that in a second. If it's visible, make sure it shows your name and also the post ID. That way, we will probably not check everyone, honestly, but we can do spot checks on that. If you're using Macs or Windows, hopefully you're familiar with how to just take a partial screenshot. So you can just do a partial screenshot like this if you're using a Mac, and then paste it over there. All right, and then paste it into the document and then just directly upload the documents, okay? So obviously don't upload from both 5 or 10, you either request for 5 or 10%. Right? If you upload for both, we will only take the 10% one. You won't get 15. Okay, so there are 2 types of posts. You either, you have posted a question or you have posted some reply, right? If you post a question, you should be able to see both your name and also the ID, the post ID. So make sure these 2 are visible when you take the screenshot. If you're doing a reply, for some reason, it immediately shows yourself as anonymous, and it won't show your name. So just make sure you have the ID over here. But on our end, if you have chosen anonymous to classmates only, that option, on our end, if I go to this post, if I put this in the URL and go to this post, I'll be able to verify that is you. Okay. Any questions about this? So it's up to you if you want to do it along the course. I recommend just doing it once at one go in the end. Actually, there's pros and cons. If you want to do it along the way, then when you get up to 10, you know your pressure is off, and so I'll leave it up to you to decide whatever works. Any questions about this? Okay, a private question. Does it count if we reply under our own post? Good question. Let's put it this way. If you post a question and then after a while you figure the answer out before someone replied to you, and then you post an answer to your own question, that's fine. Okay, so if you in the sense that, but almost in that sense, I would trust you guys to be, use it, don't sort of just spam it for the 10 posts. I'm sure you guys would have more than 10 questions, right? So if you do reply to your own question, reply it almost assuming someone else asked that question and you're explaining that to someone, because there's very likely someone else does have that exact same question and is wondering and it's hoping someone to reply. So if you give a sloppy reply, they would be disappointed, right? So, and if you figured it out, share that with the class as well. That will benefit, and I will I'll allow that. Okay. I'll trust you guys to make it responsibly. And I can see your screenshots. I can see how reasonable they are. Most of the time, I mean, it shouldn't be a problem. Okay. And also, there's also a very strong reason for me to believe in not curving the scale, so that I won't say that there's only 40% of you guys can get A's. So that really is the best way to discourage community work and helping each other out, right? You're helping each other out with that, potentially making your chances of getting an A less, and I really don't want that. So as long as you put in all the work, you guys will be able to get A. So help each other out. And helping other, first of all, it won't disadvantage you. And in fact, it really benefits you. As I emphasized on the first lecture, teaching is very, very good way to test your own understanding. As soon as you try to explain something to someone else, you realize how well or how not well you understand the topic. When is the last day to earn the extra credit? That is on the course timetable. I forgot if it's a Sunday or a Saturday. I think it's the Sunday before the final. Something like that. So just check the course timetable on the homepage and answer it.